Hello, Chem students. Let's get started with talking more about the mole today. We're going to do just a continuation of the lesson 8 where we left off on the mole. So if you'll get out your study guide, turn to lesson 8, and then flip to percent composition. That's where we'll start this discussion today off. And we'll just be talking more about moles today. So let's go. All right. So percent composition, what is it? What do we mean? Well, often it is very important to know how much mass a particular element is contributing to the overall mass of a compound. All right. For instance, let me give you an example. Water. Water is not only compound, it is a molecule, okay? H2O, it has a 2-to-1 ratio you're familiar with, all right? Now, water has a mass. It's matter, it has mass and volume, okay? So water, if I put it on a balance, it's gonna weigh something, okay? Now, what creates that mass is due to the atoms that make up water, oxygen and hydrogen. And so what I wanna know is how much of the total mass of water is being contributed by hydrogen atoms and how much of the mass is being contributed by oxygen atoms, okay? And so we essentially can find what is known as the percent composition or the mass percent, okay? Now, how do we go about doing that? Well, it's easy as long as you know the molar mass. So what I would do is think about in terms, what is the mass of 1 mole of this compound, okay? If I have exactly 1 mole of water, then I'm gonna write that up here. Let me write it up here. 1 mole of water, H2O, what is that mass gonna be, okay? And we discussed this last time. I put a mole of water on a balance, it should weigh, okay, 18.02 grams, okay? Mass of 1 mole of water. And if you want to, you can go back and recalculate the molar mass of water by using the individual molar masses of hydrogen and oxygen on the periodic table, okay? I'm just skipping that step for right now. But in most cases, if the molar mass is not given to you, you're going to have to go back and calculate that, okay? So now this is the mass I'm going to use for my total, the total mass of this compound, okay? So if I break hydrogen and oxygen down now, I'm going to kind of look at, okay, well, how much of the mass of that mole of water is being contributed by hydrogen atoms. So to find that, I need to know the molar mass of hydrogen because I'm dealing with 1 mole of atoms or 1 mole of our compound, okay? Well, a mole of hydrogen has a mass of 1.01, right? But I have, that's grams per mole, right? That's from the periodic table. But I have two atoms, okay, for every mole of water, 2 atoms. So that means that I need to multiply that by 2, okay? And then what I'm going to do is divide the mass of hydrogen, the total mass of hydrogen out of a mole of water by the total mass of 18 grams per mole, okay? And then to get it into a percentage, because that just gives me a ratio between the amount of hydrogen, the mass of hydrogen to the total mass. But I'm gonna get it into a percentage, so I'm gonna multiply by 100. So I'm gonna get out my trusty calculator here and go ahead and make that calculation. So 101 times 2 is 202. And then divide that by 18.02, multiply that by 100, and I get an answer of 11.21%. Okay, so essentially what I'm saying is that hydrogen is contributing 11.21% of the total mass of our water molecule, okay, or our mole of water, okay, 11.21%. So that means the remaining percentage of mass is coming from oxygen, all right? Now, at this point, you could easily take 100 and subtract it from 11.21%, and that would give you the amount of percent of mass contributed by oxygen, okay? Or you can set it up just like this. That's what I'm going to show you so you can kind of see it this way. Oxygen is contributing 16 grams for every mole, okay? So I only have one of those oxygen, so it's just multiplied by 1. And then 18.02 grams per mole is the total, and then multiply it by 100. Again, using the trusty calculator, I have 16.00 divided by 18.02 times 100, and I get 88.79% oxygen, okay? If I add up these two percentages, of course I should get 100. So that's make sure you can do that, check that, and so forth, which we do. So what does this ultimately mean here? Well, it means that most of the mass of water is being contributed by oxygen atoms. About 88%, almost 89%, close, of the mass of water is contributed by oxygen atoms. And only 11% of the mass of water is contributed by hydrogen atoms, okay? And so that's what mass percent is, or percent composition, is just trying to give us that information about how much these atoms are really contributing to the total mass of a compound, okay? And you can solve mass percent like this for every problem, okay? So let's do a few more examples of this that are in your notes, okay? We're gonna erase this board here. All right, the first one, it says we're going to find the mass percent, this is just out of your study guide, the mass percent of sodium sulfate, okay? So what I need to do, first of all, is since I have not been given the molar mass or the total mass of this compound, I'm going to go ahead and find the molar mass, okay? So I've already did that already. And I found that the molar mass of this compound is 142.06 grams per mole, okay? Molar mass. Now again, if I was you, I would take the time to make sure you can personally calculate that. I'm just speeding things on to make things go a little bit faster with this video, okay? Make sure you can do that. Now, what I'm going to do then is find how much sodium is contributing to this total mass in a mole, how much sulfur is contributing to the mass, and how much oxygen is, okay? So for sodium, if you look at the periodic table, the molar mass for sodium, as I'm looking at it right now, is about 23.00 grams per mole. But I have two of them, so that would be a total of 46.00 grams per mole, okay, because I got the two, right? And then I'm going to divide that by the total, 142.06 grams per mole, multiply it by 100, and I get 32.38% for sodium. So again, what we're saying is 32% of the mass of sodium sulfate, that's what this compound is, sodium sulfate, 32% of the mass is coming from sodium atoms. Okay? So let's do sulfur now. Well, sulfur, there's one of those, but according to the periodic table, sulfur has a molar mass of 32.06 grams per mole. I'm going to divide that by the total, 142.06 grams per mole, and I'm going to multiply by 100, and I get essentially 22.57%. Okay, that's for sulfur. And then the rest of it, of course, is oxygen. Well, oxygen has a molar mass of 16 grams per mole, but I have 4 of them, so I'm going to multiply 16 by 4, and I get 64.00 grams per mole for oxygen over 142.06 grams per mole, multiplied by 100, and I end up getting 45.05% oxygen. Okay, so again, I can check to make sure I add up to 100, which I should. And so looking at the data here, it's telling me that most of the mass of sodium sulfate is coming from oxygen. About 45% of the total mass is oxygen. The rest, sodium and sulfur. Sulfur is contributing the least amount of mass to the total amount of mass of the compound. Okay, so again, here's the percent composition or the mass percent of sodium sulfate, how it's broken down. Okay, good. Okay, let's do the second one there. All right, so the second one we're going to use scandium nitrate, NO3. Okay, scandium nitrate. So again, I don't have the mass. It's not giving me the total mass, so I got to calculate the molar mass. And again, the molar mass is the amount of mass of 1 mole of this compound, okay, scandium nitrate. So I calculated the molar mass for this to be 230.99 grams per mole. That's the total mass that we're going to use that. Okay. So let's start off with scandium. It has a molar mass of, so Sc has a molar mass of 44.96 grams per mole. And we'll divide that by 230.99 grams per mole times 100, and I end up getting 19.46% scandium. Okay, so there's scandium. And then I go to my next one, nitrogen. Now, remember that this 3 is multiplied by the 1, the invisible 1 there. So I actually have 3 nitrogens. So I have to calculate that. So nitrogen has a molar mass of like 14.01. So multiply that by 3, and I get 42.03 grams per mole over the total of 230.99 grams per mole times 100, and that's going to give me what, 18.20%. Okay. All right, that's again for nitrogen. And then finally for oxygen, again, oxygen has a molar mass of 16.00 grams per mole. We're going to multiply 3 times 3 is going to give us 9, so we've got to multiply 9 times 16, and that's going to give us 144.00 over 230.99 times 100, and that's going to give us 62.34% for oxygen. So here again, oxygen is contributing to most of the mass of our compound, 62%. Basically, oxygen is contributing to that mass, 19% for scandium, and 18% for nitrogen. Okay? Again, that's all you do. So there's one more in your study guide. So go ahead and pause this video for a minute and work out the last problem on yourself and see if you can get the right answers. All right? So go ahead and pause that. I'm going to erase this while you're working on. All right, you should be back. Hopefully you worked out the last problem. We'll give you the answer. So you have C6H12O6, essentially glucose there, sugar. So the total percent mass for each one of these elements. For carbon, you should have calculated 39.99%. For hydrogen, 6.73%, and for oxygen, 53.28%. Okay. There again, oxygen is contributing to most of the mass, followed by carbon and then hydrogen. Oxygen seems to be our winner today. It seems to be contributing quite a bit to the overall mass of the compounds that we've looked at. Okay, and that's not always the case, but it just so happens to be today. Hydrogen being so small, those atoms weigh hardly anything. It's not surprising that only about almost 7%, not quite 6.7% really, the mass of sugar is being contributed by hydrogen. Okay, so there you go. That's it for percent composition or mass percent. Just make sure that you can do these calculations because you're going to need these mass percents for what we're going to be doing next, and that is empirical formulas. Okay, so turn to the empirical formula section in your study guide. All right, and that's what I've done. All right, and let's talk about what we mean by empirical formula. So since we have sugar up here, let's go ahead and use that as our example of an empirical formula. Okay, so this right here is referred to as the molecular formula of sugar. Okay, and we'll come back to that in a minute. What that means is that this is not just can give us a ratio, but this is really a definite number of atoms that are in this molecule. Okay, we know that sugar, or in this case glucose is what the sugar is, that glucose here has 6 atoms of carbon, only 12 atoms of hydrogen, and 6 atoms of oxygen, and those are definite numbers. Okay, if I alter those numbers in any way, I no longer have glucose. Okay, that's what makes this a molecule. Okay, but this is its molecular formula, or the real or true formula for the compound. But it's not the empirical formula. The empirical formula is the most simplest whole number ratio to this formula. Okay, so essentially what I'm going to do is take the molecular formula and I'm going to reduce it down to the simplest whole ratio. Okay, so I can actually divide each one of these by 6, and that would make this CH2O. Okay, CH2O. So this is the empirical formula. I cannot reduce it down to a simpler formula. Okay, so really what this is giving us is the true ratio between these atoms in sugar. It's telling us that we're going to have 2 hydrogens for every 1 carbon, or 2 hydrogens for every 1 oxygen, or a 1-to-1 ratio between carbon and oxygen. Okay, so this is the ratio. This right here is the actual number of atoms in our sugar molecule. Okay, so we call this the molecular formula after being a molecule, and this is the empirical formula being the simple whole number ratio. okay? So our goal right now is to actually take experimental data and calculate the empirical formula for a compound, okay? We're going to take experimental data and use it to actually calculate this empirical formula, or the ratio between those atoms in the formula, okay, of a compound. Now, you're going to actually do this in a laboratory setting where you're going to collect experimental data and use that experimental data to find the empirical formula. And it's an important lab. It's an important idea that you can do this, okay? So let's get started. I'm going to show you how to do this calculation based on using real experimental data, okay? So let me erase this. And I'm just going to use the example right out of our study guide here for this. So it says, number one, it says a compound is found to contain 46.56% iron, and that's by mass, okay? 53.44% of sulfur by mass. So what we're saying is this is the mass percent, or this is the percent composition, okay? And they got these numbers through doing some experiment with it, okay? Which you're going to learn how to do that, the experimental part, and collecting this type of data so that you can actually calculate the empirical formula, okay? So we're kind of skipping the experimental part and taking the results or the data to find the actual empirical formula. So let's start out with these percentages. Again, these percentages are by mass. So that means if I make an assumption that our compound, which I don't know what it is, I just know it's made up of iron and sulfur, that's all I know, okay, is going to have some kind of simple ratio between those two. And I need to figure that out. And I can do that knowing these mass percents, okay? So I'm going to assume that my compound is 100 grams. Now, the reason why I'm going to do that is because I know that percentage is out of 100, okay? So if I assume that my compound, I have 100 grams, I can take those percentages and automatically change them to masses in grams, okay? So I'm going to do that. I'm going to take my first one, which is iron, and I'm going to create 46.56 grams of iron, okay? So that's what I'm going to say out of my total mass of 100 grams for this unknown compound, 46.56 grams of the compound is iron, okay? That means the rest of it is sulfur. And that happens to be 53.44 grams of the sulfur, okay? So I have those written down in this manner because what I'm about to do is some dimension analysis. I'm going to convert these two masses into moles. Now you're going to do that every time. To start off with creating the empirical formula or finding the empirical formula is convert your masses of all your elements involved in the compound into moles first, okay? So I'm going to quickly do that. So to go from mass to moles, I need the molar mass. The molar mass of iron is 55.85 grams for 1 mole of iron, okay? My grams cancel out. I do my calculation, and I end up with 0.83366159. Now, I'm not going to be worrying about significant figures with my mole values. I'm just going to go out several decimal places, okay? Because you'll kind of see why in a moment, okay? Now, for sulfur, I'm going to do the same thing. The molar mass of sulfur is 32.06 grams to 1 mole of sulfur. grams of sulfur cancel out, and the moles is 1.66687 moles of sulfur, okay? So now I have the moles of my two elements in this compound. Now, if I had another element, I would do the same thing. I would calculate its molar mass, or if I had another element, calculate the number of moles for that element and so forth, using its molar mass. Now, at this point, once I have the moles of all the elements in the compound, I am going to simply find a ratio between the moles. To do that, I'm going to divide by the smallest number of moles, okay? So I look at my two moles, here are my two answers, and iron has the smallest number of moles. So I'm going to divide both of these by that number of moles. So I'm going to take and go 0.833666159 moles, divide, and that's going to give me 1, right? And I'm going to also take this and go 0.833666159, and that's going to give me, if I divide those, it should give me a 2. Okay? So the 1 and the 2 that I just calculated are going to be my subscripts in my chemical formula. That's my ratio. Okay? That's it. That's all I have to do. Now, I'm going to put it together. So I usually, by convention, put the metal first and then the non-metal. And that's going to be pretty much how we'll always do it. Metal first, followed by the non-metal. So I'm going to put Fe first. And since there's only one, it would be an invisible subscript of 1 and then S2. Okay? So 1 to 2 ratio, FeS2. This is iron sulfide, or fool's gold. Yep, fool's gold. Fool's gold is iron sulfide. Okay? And so that's basically what I've calculated there. Okay? And that's really all there is to in finding the empirical formula. Okay? So let's do the last one that's there in your study guide. As a second example, so it tells us that we have a compound that contains nitrogen, sulfur, and then the rest is oxygen, okay? So they give me again the mass percents, which we get from an experiment, okay? We get that data from experiment, which we've skipped the experiment and collected those results. Now we're going to use those results to calculate the empirical formula. Okay, so for sodium, again, I'm going to assume I have 100 grams total of this compound. So I'm going to take 36.5% and change it to grams of sodium over 1, okay? And then for sulfur, I have 25.4 grams over 1. And then finally, the rest of it is oxygen. So and remember, I have a total of 100 grams. So I'm just going to add these two up, subtract that from 100, and I should get the mass of oxygen, which turns out to be 38.1 grams of oxygen over 1. Okay. Now again, I'm going to find the moles. So I'm going to use 23 grams of sodium to 1 mole. Again, that's the molar mass of sodium. That is an answer of essentially 1.586956. For sulfur, 32.06 grams of sulfur to 1 mole of sulfur. That's going to give me an answer of 0.79222645. And then for oxygen, it's 16 grams of oxygen to 1 mole of oxygen. And that leaves me with 2.38125 moles. Moles and moles. That's again a sodium, this is a sulfur, and this is oxygen. Okay, so now again I have my moles of each of the elements in this compound, okay, which is only 3 elements. Now I need to find the ratio between them. So I'm going to divide by the smallest number of moles, which happens to be sulfur, right? So I'm going to divide everything by 0.792264. That's going to give me 1. This one, 0.792265. That gives me 3. And this one is going to be 0.792265, and that's going to give me 2. Okay? So there's my ratio, 2, 1, 3. So now all I have to do is create my empirical formula. Again, I put the metal first, which is sodium, followed by my nonmetals. Okay, now the question is, which nonmetal goes first? Well, we'll get more into that. For right now, I'm not going to be really picky, but technically, I would put my sodium first, and that would be Na2, right? And then I would go ahead and go with sulfur, which is 1 sulfur, and then my oxygens is 3, okay? So that would essentially be my formula, empirical formula is Na2SO3, okay? This compound being known as sodium sulfite, okay? And that's it. That's essentially what I would have to do, and I'm done with finding the empirical formula, okay? Now, there will be more complex problems that will arise over time in order to use some data from experimental data to solve for the empirical formula. And so we'll study some different versions or different types of problems with empirical formula. Okay, that's it. Okay, good? All right, awesome. Now, there really is only one last thing we need to discuss, and that is, okay, what about those molecular formulas? So if I have the empirical formula, how would I calculate the formula? Okay, well, honestly, you need the empirical formula to calculate the molecular formula in many cases, okay? Depending on the experimental data that's given to you, okay? So let's go turn in your study guides to the molecular formula section. And remember, we've already had a discussion with sugar that C6H12O6 is the formula for glucose, the type of sugar, okay? That's the molecular formula, okay? And I might even write that down. That's the molecular formula for glucose or sugar. The empirical formula, remember, says we reduce that down to CH2O. Okay, so that's our empirical formula. Okay, let me write that E better. Empirical formula. Okay, now in order to find the molecular formula, we need to have that empirical formula. And then we take that empirical formula and determine this, okay? So usually we'll get experimental data to give us, to allow us to calculate the empirical formula, and then we can go a step further to find the molecular formula, okay? So that's what we're gonna focus on, is finding that molecular formula. So we have a problem in your notes that basically says, hey, we have a compound. It was found that we have a compound that has a molar mass of 91.1 grams per mole, okay? 91.1 grams per mole, okay? This really is the formula for the molecular, or the molar mass for the molecular formula, okay, of our unknowns, okay, compounds. And I have to have this, right? This is a must. In order to figure out the molecular formula, I need to know the molar mass of the molecular formula. So that's given to you, usually found through experimental, okay? Again, we're skipping the experiment, going right to the data, okay? But what it does found is that the compound contains 0.608 grams of nitrogen and 1.3388 grams of oxygen, okay? So those are the masses of the elements in my compound, okay? Now what I can do is I don't have the percent composition like I did in previous problems, but I can go ahead and use these masses just as they are and use this to find the empirical formula. So all I'm going to do is take these masses and convert them into moles, okay? So I'm just going to do that quick. So nitrogen has a molar mass of 14 grams per mole, oxygen 16 grams per 1 mole. Okay, again, all I'm doing is finding the number of moles. So this is 0.0431205674. Remember, I'm just going to go out to some decimal places here. This one, okay. So these are the moles of these two elements, okay, that are in the compound, or unknown compound. So now I divide by the smallest number of moles, which happens to be 0.04312056, you know, you get the idea, and 0.0431205674, okay? What does that equal? Well, that's equal to 1, and this one is equal to 2, okay? So what that tells me, that's the ratio of nitrogen to oxygen in my empirical formula. So that would be NO2, okay, if I put it together. That is, again, the empirical formula, not the molecular formula, okay? So now I still need to find the the molecular formula. So all I'm going to do is find the empirical formula's molar mass now. So I calculate that, I've already done that, to be essentially 46.01 grams per mole, okay? And you can calculate that using the periodic table, just like any other way to find molar mass, okay? So here's my molar mass for the empirical. Here's my molar mass for the molecular formula. Again, this is given to me by the experiment, okay, or in the problem. This I found by essentially finding the empirical formula, okay? So now what do? Well, I am going to find the ratio between these two masses. So I'm going to essentially take 91.1 grams per mole, that's the molecular formula's molar mass, and divide it by 46.01 grams per mole, which is the empirical formula's molar mass. And I end up getting a 2.0 ratio, or ratio of 2 between those two masses, okay? So now what do I do with this 2? I'm going to take that 2 and I'm going to multiply it by these two subscripts, all right? So I'm going to take nitrogen and multiply it 1. There's an invisible 1 there, right? So 1 times 2 is 2, and then 2 times 2 is 4, and I have now my molecular formula, and that's it. That's all I have to do, okay? And my molecular formula. Notice I can reduce this down to my empirical formula of NO2, okay? So again, the process, I essentially take my experimental data, the mass of each of the elements, find the number of moles, divide by the smallest number of moles to find the empirical formula, find the molar mass of the empirical formula, and then find that ratio, divide the molecular formula, molar mass, by the empirical formula's molar mass, and then I take that ratio number and multiply it by the subscripts in the empirical formula, find the molecular formula. Okay? That's it. That's all there is to it. okay? Now, what I think you should do is try to do the last one on your own, okay? So pause this video and see if you can actually figure out what the empirical formula is, and then find out what the molecular formula is by using this similar process, okay? So pause it, I'm gonna erase this, and then when you're done finding it, turn the video back on and I'll have the answer for you, okay? All right, you should have had plenty of time to do it. Now listen, I know you can just copy the answer, but it does you no good, okay? It's important that you can actually solve these on your own. So please, even though I'm giving you the answer, go back and make sure that your answer matches mine and that you can get there, okay? So what I found, the empirical formula, this is again for number 2, was C3H4O3. That's the empirical formula. And then all I did was find that the molar mass of this was 88.07 grams per mole. Okay, I calculated that. The molar mass of the molecular formula was given. So that was like 180 grams per mole. That's the molecular formula's molar mass. And I took that 88 grams per mole of the empirical formula's molar mass. I found that to be what? 2. And so then what I essentially did is multiplied that 2 by these, and I got C6H8O6. And that's the molecular formula for the last problem, number 2 in your study guide, okay? So that's it. Hopefully you calculated the empirical formula correctly. If you didn't, and we can talk about it, or come and see me and we'll discuss it, okay? Good? Awesome. Well, really, that's kind of our conclusion for lesson 8, the mole, okay? We're not done with the mole by any means. We will be studying moles actually in the next lesson as well, when we talk about solutions and solution concentrations and so forth. But we will be we're going to spend an entire unit on the mole itself. We're going to be talking about what is known as stoichiometry. And that is a really hallmark unit for chemistry, very important, okay? So we'll get there. So for now, study what you've learned about the mole, and yeah, we'll get more into it later on. So I'll see you for now. Have a good one.